Hello everyone and welcome back. Today we're going to start talking about torque, which in and of itself is actually part of a much larger physics topic called rotational motion. Now torque is probably a term that you've heard before, but a lot of people don't have a good basic understanding of what it is. So I'm going to start with that. And to do that, I'm going to bring out a ramp. Now a ramp is something that we have discussed before in earlier lessons. So I'm going to do a comparison. We're going to have this block here, which is the exact same block at the exact same height, and the goal is to lift it or push it up the ramp to an even higher height. Now we're going to do a force diagram. Force earth on block. Force earth on block is going to be the same for both of them. Now let's talk about lifting it. So if you want to lift this block on the right straight up in the air, I'll do force person on block. If you want to lift this at a constant velocity, force person on block and force earth on block would have to be equal. The initial force on the person would have to be a little larger than force earth, but once it starts moving, Newton's first law states that if the forces are balanced, the velocity will be constant. Now, let's take a look at the ramp. We're going to say it's a frictionless ramp. So you have force perpendicular, force parallel, but no force friction. I'll also add force normal from the ramp. Now, in the case of the ramp with friction, the force you'd have to match is force parallel. Force earth is broken up into these two. So this is force person on box, which means, and hopefully you remember this from before, in order to lift the box straight up into the air, you would need a lot more force than if you were using the ramp. It's actually the whole purpose of using the ramp in the first place. One way to put it is by taking a quick look at the work equation. Work is transfer of energy to or from the system, and you are transferring gravitational potential energy to the system. And there are two ways to do this. If you lift it straight up in the air, you need to match force earth. If you want to push it up the ramp, you need to match force parallel, which is a component of force earth, which is why it's a lot smaller. And since you're lifting it to the same height, you need to transfer the same amount of gravitational potential energy. That also means that if the ramp is 4 times as long as the height, you would only need 1/4 of the force, which is the whole purpose to using a ramp in the first place. In other words, using less force by using the ramp is a huge benefit. However, the downside is you need to push it 4 times the distance. In most cases, however, that is a disadvantage most people would very easily take. Now, I'm going to put this side by side with a door. This is an above view of a door. This is the hinge right here, and it opens this way. So we're going to say the goal is to open this door 90 degrees. Now, something I want to know right now. We say in our language, open the door. But what you're actually doing is rotating the door. That's going to be an important point here. Now, taking that idea, right here approximately is the center of mass of the door. We're going to try to move that to here. So the center of mass of the door is going to move through this distance, which is also called an arc length because it moves in a circular path, but I'm just going to use d for distance. Now, here comes the important part. You can push on this door anywhere you want. You can push it far away from the hinge. You can push really close to the hinge. You have a choice. With the box, we were pretty much assuming you were pushing right through the box's center of mass. But now it's not the case. You have a choice of where to exert your force. Now let's take a look at 2 options. First, we're going to take a look at option far away toward the edge of the door. So I'll call this option A. Now, if you push at point A for the entire time, you're going to exert a force approximately over this distance. Not a very good looking curve, but you get the idea. Or you could push at position B, which I'll put right here. If you push at point B, you only push for this distance. Now, something else I want to make clear at this point. You're not just opening the door. You are accelerating the door. The door started at rest, and you speed it up until it is at 90 degrees. Now, in both these situations, we're saying the door has the exact same angular velocity, exact same final velocity here. So in other words, everything's the same as far as kinematics is concerned. The only difference is where you're pushing on the door. Now, to relate it back to here, in order to accelerate the door, you need a force. The distance the center of mass of the door is moving is not changing, because no matter where you push, the center of mass of the door is not changing. Now, here's where the connection comes into play. If you push at point A, you are exerting the force over a much larger distance, much like pushing this box up the ramp. Therefore, if you're exerting the force over a larger distance, you need less force to open this door. If you push at point B, you're exerting a force over a much smaller distance, kind of like taking that box and lifting it straight up into the air. If you're exerting the force over a smaller distance, then you require much more force to do so. So in other words, our connection to work or transfer of energy is very similar in these two situations. In the first situation, you're gaining gravitational potential energy. In this situation, you're gaining a type of kinetic energy. Because again, the door is getting faster as you open it. It starts at rest and you speed it up. Now, what that comes down to is this. In order to rotate an object, like opening a door, it's not just the force that's important. How far away you are from the axis of rotation is also important. The farther you are away from the axis, the less force you need. So you need a force and you need a distance from the axis, which, if you notice the kind of circular patterns you're making here, is typically called a radius. And we're going to get into a little more of that in a moment. So to boil this down to one statement, to accelerate something in a straight line, you require a force. However, to accelerate something rotationally, you require a force, and you need that force to be a distance from the axis. And we call that a torque. So before I get into the nitty-gritty here, we're going to start with the word of the day, torque. Now, if you look online in the dictionary, you'll see a pretty simple definition about using a force to rotate something, blah, blah, blah. But I'm going to get a little more specific here, and this will help your memory for when you need it. So we're going to use this. Torque, the rotational equivalent of force, a quantity needed to give an object an angular acceleration. So a force is needed to give an object a linear acceleration. A torque is required to give an object an angular acceleration. While we're here, I'm going to give you a few more. Second definition I want to give you is lever arm, the distance from the axis to the perpendicular force. You're going to hear me using this word as I do a few examples. Now, the lever arm is sometimes referred to as a physical object, and sometimes it can be. So talking about the door, someone could say the door is the lever arm. However, the lever arm is just the distance you're using between the axis and the perpendicular force. Nothing actually has to be there, and I'm going to talk about that as well. The third one is axis of rotation, the only point on a lever arm that does not move. For example, in the door example we just did, or when you actually open or rotate a door, the only part of the door that does not move is the axis. And that also brings up another point. If I go back to my door, or you walk to your bedroom door, and you start exerting a force on the hinge, is that door going to open? Well, the answer pretty obviously is no. You can push on the hinge of the door all day, it's not going to open. In other words, the door is not going to rotate. You can exert a force on the hinge all you want, but you do not have a torque unless you have that distance from the hinge. So to rotate that door, you require both of these. This idea is really common in mechanics, so let's bring up a very simple example. Let's talk about a wrench. So here I have a bolt, let's say a lug nut on your car or something similar, and it's really, really stuck. Now our goal is to rotate this bolt. And once again, we want to rotate it 90 degrees. So you want to take this wrench and you want to rotate it around to loosen up the bolt. Lefty-loosey, righty-tighty. Now you only have so much strength, so you don't really have much choice in that. However, what you do have a choice on is where you grab this wrench. And since we're talking about rotating the bolt, it requires a certain amount of torque to actually rotate that bolt. So you have a choice. Do you want to grab the wrench at A, at B, or at point C? Well, if you said point C, you were definitely correct. As I said earlier, the downside of point C is you have to push this over a larger distance. However, most people don't care about that. That is a downside people will very easily take in order to use less force. Also, the distance to force, just like the ramp, is a perfect ratio. So if C is 3 times the distance away from A, you need 1/3 the force. So now that I'm at this point, let's actually talk about the math, which is kind of simple. The torque symbol is tau, or the wavy looking T, is force perpendicular times radius. Not to be confused with the work equation, which is force parallel times displacement. So this perpendicular part is going to be very important. Perpendicular to what? Well, the answer is to your lever arm. And the lever arm may or may not be referred to as a physical object. In this case, I would say the lever arm is literally the handle of the wrench. You exert a force directly this way in order to rotate that wrench. And as you can see, if I'm producing the same torque in this situation, if the radius is 3 times as large, then the force can be 3 times smaller to get the same answer. The units for torque are quite simple. There are no special units. You take force and you take radius and you take the units for each. Force is newtons and radius is meters. So the unit for torque is the Newton meter. A little side note, in America, the unit for torque is the foot-pound, where foot is the radius and pound is the force. There is one more thing to note, and that is torque has a direction. Now, looking at this picture, there are really only 2 directions to go. You can either rotate this counterclockwise or clockwise. Those are the only 2 directions in a first-time physics course that you will only really be dealing with. And as far as directions are concerned, much like directions we did for kinematics, they are dealt with as positive or negative. Which way is which? Well, they follow the exact same system as the unit circle. And you may remember this from math class. Starting at 0, going around this way is considered the positive direction or counterclockwise. So if you rotated it clockwise and the numbers get smaller here, then it is considered the negative direction. Clockwise is positive, counterclockwise is negative. That's it. Now here's the rub on this. You have to do this part visually. It does not come out in the math. In other words, if I take a wrench here and flip it, now again, I want to loosen this bolt. I'm going to grab the handle right here. I'm going to exert a force this way, which is downward. Now, based on our standard directions, up is positive, down will be negative for force. However, when it comes to torque, you're going to completely ignore that to a degree. Let's say the force is 10 newtons and the radius or lever arm distance is 0.5 meters. Torque is force perpendicular times radius. This force is downward. Now, typically, I would say that's a negative force. However, this would rotate it counterclockwise, which for torque rotationally is a positive torque. So it'd be 10 newtons times 0.5 meters, and you'd have a torque of 5 Newton meters. Now, more importantly, I'm going to reverse this. Now, I'm going to say the force is upward. So again, force is 10 newtons. Well, our equation here is exactly the same. 10 newtons times 0.5 meters. However, looking at my image here, this would rotate clockwise. That would therefore make this a negative torque. In other words, you need to do the positive or negative visually. You need to have either a sketch or a visual image of the situation. Ask yourself, which way is this going to turn? If the answer is clockwise, it's negative. If it is counterclockwise, then it is positive. All right, let's end up with a few examples here. So I have this wrench. I'm going to say the distance to where you grab the wrench is 0.8 meters. Pretty long wrench, but whatever. Now, optimally, you want to exert a force this way, but I'm going to say you don't do that. You exert a force in this direction. And once again, I'll say this force is 50 newtons. Now, torque is force perpendicular times radius. So what do you do? Well, I'm going to go back to a statement from my earlier lectures, which is, if you ever see a vector at an angle in physics, you're always going to break it up into its component pieces. Typically, that was if the force is at an angle to the surface. However, in this case, it is true if the force is at an angle to the lever arm. So I'm going to say this angle theta is 30 degrees. And making a vector breakup for a force, you're basically making what is a right triangle with vectors. Do not forget the arrows. A little side note, you may want to ask your teacher whether or not they want the arrows on the component pieces, because technically the AP exam does not like these. However, a solid line and dashed line should be a good visual for what is the actual force and what are component forces. So here's a base equation, but we do not have the perpendicular force. The perpendicular force is here. How do we get it? Well, it's kind of simple. We have the hypotenuse. We know the angle here. This is the adjacent side. Therefore, force perpendicular would be F cosine theta. which means my torque in this situation would be F cosine theta times radius. 50 newtons cosine 30 degrees times 0.8 meters. And I would get positive, because again, it's going counterclockwise, 34.6 Newton meters as my answer. So I wanted to show this example because if you do not have the perpendicular force, you simply need to find it. And a small note on this. On the AP exam equation sheet, if you look at it right now, it will say force sine theta. However, that is only true if you're using the angle that is actually touching the lever arm. So if I gave you alpha here and I split this, the opposite side would be here and they'd be using sine theta. However, if an examiner wants to see if you know what you're doing, the first thing they'll do is put that angle on the opposite side to see if you're actually following how to get the perpendicular force or if you're just following the equation on the page. So my advice here is pretty much the same for my advice for any other topic. Draw it. Draw it, take a good look at it and say, how do I get the perpendicular force? What direction is it rotating? That's the information you need. All right, I'm going to end this with another example, and I'm actually going to do this twice for a very particular reason. I have my same wrench. It's on a bolt. Instead, this time, in order to rotate this bolt clockwise this time, I'm going to hang something from this. Typically, you would get the weight by using mg, but we're just going to deal with this in terms of force earth. I'm going to erase a little section of the wrench. To make our angle more clear, this is theta, and you have distance d. All right, let's put in some numbers so you can follow along with me if you want. I'll say force earth is 60 newtons. I'll say theta is 40 degrees, and I'll say distance d is half a meter. All right, there are two ways to do this. First way, this force earth, is downward. It is not perpendicular to the lever arm, so we're going to split the force. I'm going to split it this way and this way. So literally, again, force perpendicular, force parallel. Force parallel we don't need. We want the one perpendicular to the lever arm. Now this breakup looks very similar to the ramp breakup, actually. If I was to follow these two lines here, they make a nice 90 degrees. If this is 40, this would be 60 degrees. Therefore, this angle in here would be theta, which is 40 degrees. Force perpendicular, therefore, would be force earth. Again, it's adjacent cosine theta. So torque, force perpendicular times radius. So our full equation is going to be force earth on object times cosine theta, because that's perpendicular force, times d, which is our lever arm distance between the axis and the perpendicular force. 60 newtons, cosine 40 degrees, times 0.5 meters. And I would get, and this is important, a negative, because again, the negative does not come out in the math. There's no negative here. However, looking at my picture, this would rotate clockwise, which via the unit circle is a negative direction. So this is a negative torque. Negative 23.0 Newton meters with the rounding. Now, I'm going to cut this off, and we're going to do this again. Only we're going to use a slightly different technique because there is something I wish to show you. First, force earth goes downward. We're going to take it. I'm just going to extend this line. Then, here is the axis of rotation, dead center of the bolt. I'm going to take an imaginary line, bring that to the right, and I hit that force at a right angle. Now I'm going to go back to our lever arm definition, which states that the lever arm is the distance between the axis and the perpendicular force. In our last problem, we used d as our distance. Only this time, we're going to use this distance, or I'm simply going to call r. And since this distance is perpendicular to the force that's being exerted, it still obeys the rules. It's still perpendicular. And if we look at this picture here, it's basically one big right triangle. Seeing that r is going to be d cosine theta, because this is the adjacent side. Torque is force perpendicular times radius. Force perpendicular is force earth on object, times my lever arm distance is now d cosine theta, which if you look, is exactly what I have up here. In other words, if I follow through in this, I'm going to get the exact same answer. But the bigger deal is this. As long as the force and the lever arm distance are perpendicular, it will work. You can either break up the force like you did earlier, or you could break up the distance, whatever is easier to see. From my point of view in this example, breaking up the forces is a little bit rougher. You got to do the extra angles and stuff. where breaking up the distance in this case just seems a lot cleaner. You could do either, but I want to be clear to let you know that you have the option. As long as the force and the lever arm distance are perpendicular, you will find the torque. And again, counterclockwise is positive, clockwise is considered negative. Therefore, I have a negative torque here. All right, that is the basics for torque. I'm going to pause here and get into some more details next time. Have a good day. This is Mr. M signing off.